This video is the third in a series on the Echelon algorithm and provides a behind-the-scenes look at Echelon segmentation. This demonstration will show how Echelon segmentation works by applying the process to a single frame of video. Prior to performing segmentation, colour and lighting effects are normalized. The image is then blurred multiple times as shown here, and the blurry tiers are stacked one on top of the other, resulting in a 3D volume of pixels. When we look at an image, we perceive visual information in a spatial domain comprised of two dimensions, x and y. The blurring step, demonstrated earlier, establishes a scale space image which includes a third dimension, referred to as scale. The scale axis defines a scale domain inside the 3D volume of a scale space image. Within the scale domain, visual details assume the form of stationary points, locations where the intensity is either a local maximum or minimum, shown here in a single scale domain tier using black and white dots. Moving from one tier to the next in the scale domain, the density of stationary points decreases as shown here. Next, a single stationary point, indicated here with a yellow circle, will be used to demonstrate the natural mechanism responsible for the decrease in point density as blurring, or scale, increases. The solid lines shown in this scale space tier are referred to as isocontours. They correspond to paths of constant intensity and have been added to help clarify the demonstration. As the animation cycles, notice that the circled point migrates toward and is then absorbed by a parent stationary point. All stationary points in the scale domain are guaranteed to share the same fate as the one chosen for this demonstration. In the literature, this generic fate is referred to as an annihilation event. Annihilation events act as beacons that mark locations in the scale domain where stable visual information can be harvested to support recognition. This stable information is embedded in each vector that corresponds to a natural association between a child and parent stationary point, as shown here with a red arrow. At annihilation, each child stationary point is also naturally associated with as many as two parents with the opposite polarity, as shown here using green arrows. These additional associations represent additional stable information available to support recognition. To summarize, the decrease in point density as scale increases is due to stationary points merging with parent points as a result of generic annihilation events. Annihilation continues in all images until only a single point remains, as highlighted here with a yellow circle. The natural parent-child associations that exist as a result of annihilation events establish a scale space tree, further clarified next. The branches in a scale space tree are oriented normal to the image plane and intersect each scale space tier at a stationary point. To demonstrate this, the yellow circle shown here will trace a single branch through the scale domain from its base to its tip. The view shown here is the first tier in the scale domain. Each dot corresponds to the tip of a separate branch in a scale space tree. Remarkably, every branch in every image ultimately merges into a single trunk, such as the one shown earlier. The animation will now trace the same branch from the first tier toward the point where the branch joins its parents. Such a junction point is referred to in the literature as a top point. The term top is used because top points lie at the largest scale within a branch. The parent for the current branch are indicated here with red and green arrows. The associations between a child branch and its parent are not arbitrary. Rather, the associations exist as a result of natural paths determined by local intensity gradients. This is clarified in the right-hand image by adding isocontour lines and showing the actual paths that link a top point to its parents. The branch traced earlier using a yellow circle is reconstructed here as a curve comprised of discrete points. In the literature, such curves are referred to as stationary curves. As in this example, all branches in a scale domain tree intersect the spatial domain at points referred to as interface points, shown here as a red dot. Interface points lie at the boundary between the spatial domain, that which we perceive, and the hidden scale domain, where visual information assumes a more stable form. So far, the demonstration has focused on a single branch within a scale space tree. Next, the demonstration will show the architecture for a portion of a scale space tree, referred to in the literature as a cluster. The example cluster will be extracted from the subblock corresponding to an eye region, as shown here. Echelon segmentation is based on an error-free blueprint that is naturally encoded in a scale space tree. This naturally encoded blueprint has 6 key components. Interface points, shown here as enlarged dots, represent the first component in the blueprint. Interface points provide precise locations for each feature region in an image. Top points represent the second component in the natural blueprint. Each branch in a scale space tree connects one interface point to one top point. Top points mark locations in the scale domain where stable local descriptors can be extracted and used by a computer to memorize sites so they can be recognized later. The third component in the naturally encoded plan is linking between child and parent branches. The Echelon algorithm uses the natural links that exist between branches to combine local descriptors into all-view object models. The fourth element in the naturally encoded plan is feature polarity. All images can be regarded as contiguous collages of dark and light regions. Light regions embody positive polarity, dark regions negative polarity. Polarity is encoded in a scale space tree as positive when a branch is made up of local maxima, or negative when a branch is made up of local minima. Feature polarity is used by the Echelon algorithm to separate dark features from light features during recognition and classification tasks. The fifth component is relative feature region orientation, as represented here by the varying angles at which each branch joins its parent. Orientation information embedded in a scale space tree endows echelon descriptors with high classification strength. Finally, the naturally encoded plan provides a unified definition for a feature region, clarified next by taking a closer look at the feature regions corresponding to an eye. This enlarged view shows all interface points in the vicinity of an eye. Among the set of all interface points around the eye, the subset shown here in red is responsible for establishing the eye's shape or outline. To clarify this point, the demonstration begins with a single interface point, shown here as a red dot. Each interface point corresponds to a natural feature region, shown here using green. Natural feature regions are defined by the boundaries that divide light from dark in an image. The animation continues by showing how natural feature regions combine like pieces of a puzzle to establish whole objects, in this case an eye. The entire spatial domain is contiguously tiled with interlocking feature regions that combine naturally to form unbroken outlines around what we perceive as objects, in this case an eye. In summary, echelon segmentation is based on a naturally encoded plan available in all images. The plan links feature regions in the spatial domain into whole objects and enables autonomous all-view learning, as further described in the next video in this series. Thank you.